Why did steam locomotives grow from compact four-wheel switchers to giants like the Big Boy? The answer isn't just size, it is the hidden math of steel, friction, and physics that dictated exactly how big, how powerful, and even how many wheels a locomotive could have. Each breakthrough rewrote the rules for what trains and industries could achieve. But almost no one understands the logic behind those wheels. If you are ready to uncover the engineering secrets behind the world's most iconic machines, hit subscribe. Because the real formula starts with a single idea and ends with the biggest locomotive America ever built. Every locomotive's pulling power starts with a single, stubborn limit: adhesion. No matter how big the engine or how many wheels it has, the rails only allow so much force before the wheels slip. The basic formula is simple. Tractive effort equals the coefficient of friction, called mu, multiplied by the weight pressing down on the driving wheels. On a dry steel rail, mu averages about 20%. That means a locomotive with 100,000 pounds on its drivers can put about 20,000 pounds of force into the train before the wheels start spinning uselessly. Engineers learned early that the real trick was not just adding more wheels, but putting as much weight as possible on the powered axles. This is why the earliest switchers, like the 040, put every pound right over the drivers. But there is a catch. Too much tractive effort, and even the best steel tires will break loose. To keep things safe, designers aimed for what they called a factor of adhesion around 4. That means the locomotive had 4 times more weight on its drivers than the force it tried to put into the rails. Any less, and the risk of slipping grew, especially on grades or when rails were wet or greasy. Bar charts comparing classic switchers to later freight engines reveal the difference. A 040's compact weight gives it excellent grip for its size, but when heavier loads arrived, engineers needed more axles to spread the weight without losing that vital connection between steel wheel and steel rail. The logic of adhesion would shape every wheel arrangement that followed. Every steam locomotive rides on a frame that keeps its wheels locked in a straight line. That frame, the rigid wheelbase, sets the rules for what a locomotive can and cannot do on the rails. With a 040, the distance between the front and rear driving axles is short, often just 8 to 10 feet. This compact setup lets the locomotive twist through tight industrial curves, sometimes with a radius under 200 feet. The wheels follow the track easily, and the flanges, those raised lips on the inside edge, rarely grind too hard against the rails. But as soon as designers stretched the wheelbase to hold more weight or add more driving wheels, a problem appeared. A longer, rigid frame, like the 14 to 16 feet found on a 060, means the wheels cannot pivot to follow the track. On sharper curves, the outer wheels want to keep going straight, while the rails demand a tighter turn. The result is a battle of forces, steel flanges scraping against steel rail, building up stress that can lift a wheel clear off the track or even cause a derailment. In real yards, this meant a 060 might struggle with curves that a smaller 040 handled with ease. Engineers tried tricks like thinning flanges or giving axles a bit of sideways play, but these were only partial fixes. The basic geometry was unforgiving. The longer the rigid wheelbase, the larger the minimum curve radius needed, sometimes more than 400 feet for a mid-sized switcher. This barrier set a hard limit on how big or powerful a rigid frame locomotive could get before it simply could not handle the track. The logic of the wheelbase would push designers to look for new solutions, ones that could guide heavy locomotives smoothly around the bends that defined real-world railroads. By the turn of the 20th century, American railroads faced a bewildering variety of locomotive designs. Each railroad had its own way of naming and describing wheel arrangements, making it hard for engineers and crews to communicate across regions. In 1900, Frederick Methvan Whyte, a mechanical engineer with the New York Central, introduced a simple, universal way to describe steam locomotives. Count the unpowered wheels in front, the powered driving wheels in the middle, and the unpowered wheels at the back. A 280, for example, has 2 leading wheels, 8 drivers, and no trailing wheels. This system, now called Whyte notation, quickly became the language of American steam, letting anyone, shop foreman or timetable clerk, know at a glance what a locomotive could do. The 280, known as the Consolidation, was the first great beneficiary of this new clarity. Introduced in 1866 by Baldwin, it answered the freight demands of a country moving more coal, grain, and raw materials than ever before. The key was the 2-wheel leading truck. Unlike earlier designs where every axle was locked rigidly in line, the leading truck could pivot, guiding the locomotive smoothly into curves and reducing the side forces that plagued longer, heavier engines. With 8 driving wheels gripping the rails, the Consolidation delivered massive tractive effort, yet could still handle the winding main lines and rough track of the post-war boom. Over 18,000 were built in the United States, making it the most produced freight locomotive of its era. The Whyte system gave this family of designs a clear identity, and the 280 became the backbone of American freight, its geometry both a product of and a solution to the challenges of a growing nation. Passenger railroading in the early 20th century demanded more than brute force. As trains grew longer and timetables tightened, speed and reliability became the new benchmarks. The 462 Pacific emerged as the answer. Its secret was in the rear. 2 trailing wheels supported a much larger firebox than any previous design. Earlier locomotives, even with powerful engines, struggled to fit enough firebox above the driving wheels. There simply was not room to burn enough coal for the higher steam output needed at sustained speeds. The trailing truck solved this elegantly. By shifting the firebox behind the drivers, engineers could expand the grate area by 20 to 50%. That meant more fuel could be burned, more steam generated, and more power delivered to the rails, hour after hour, mile after mile. Trains could now glide at 60 or even 80 miles per hour without losing steam pressure, a feat that had been out of reach for most earlier engines. Railroads quickly recognized the advantage. The Pacific type became the dominant passenger locomotive across North America, pulling flagship trains like the Pennsylvania Railroad's Broadway Limited and the Southern Pacific's Daylight. The combination of a 4-wheel leading truck for guidance, 6 powerful drivers for traction, and a trailing truck for firebox support created a layout that balanced speed, stability, and endurance. It was not just about going faster. It was about keeping schedules, meeting passenger expectations, and making long-distance travel smoother than ever before. The Pacific's wheel arrangement set a new standard for what a passenger locomotive could achieve. By the late 1930s, railroads demanded a locomotive that could do it all, hauling fast passenger trains and heavy wartime freights with equal confidence. The answer was the 484, known as the Northern. With 4 leading wheels for steady tracking at speed, 8 massive driving wheels for grip, and 4 trailing wheels supporting a firebox big enough to feed the largest boilers yet, the Northern became the backbone of mainline service across North America. Its design struck a rare balance: enough adhesion to move long trains, enough steam to keep up mile after mile, and stability for running at 90 miles an hour. Railroads like Northern Pacific and Santa Fe put these engines at the front of their flagship trains, trusting them with everything from troop transports to express passenger runs. The Northern was the final word in rigid frame steam power. Any bigger, and new solutions would be needed. When the mountains of the American West pushed rigid locomotives to their breaking point, Union Pacific turned to a new answer: articulation. The big boy, introduced in 1941, was not just big for the sake of spectacle. Its 488 4-wheel arrangement split the driving wheels into 2 hinged engine units, each able to pivot independently beneath a single boiler. This allowed a locomotive more than 132 feet long and weighing over 1.2 million pounds to snake through the curves of the Wasatch Range, hauling trains that once needed 2 or even 3 engines. 25 big boys were built. Each was designed to pull 3,600-ton trains up 2% grades without helper engines. The logic was simple but bold. Solve the limits of rigid frames with a flexible, articulated design, and conquer the steepest main lines with a single unified machine. Every wheel arrangement you see in a preserved locomotive today is an answer to a real engineering puzzle. Not a relic, but a solution forged by physics. As technology races forward, the logic behind these giants still shapes how we solve problems in motion. Thanks for watching.